All right, so good morning, everyone. Today we're going to talk about the OWASP Top 10 Mobile Risks, or maybe we should have put the subtitle in there, why security people can't count to 12. I know everybody likes 10, so that's kind of what we went with. All right, so we're going to do brief introductions. We're going to do just a little bit of background information on the Mobile Security Project, why it happened, and what we're trying to achieve. We're going to cover the mobile threat model at a real high level, just kind of talk about the attack surface for mobile apps, what makes them unique, and where you need to think about applying controls. We're going to get into the actual top 10 themselves, and then every time we have left, we're going to do some Q&A, and then we're going to take it into the Q&A room after this. So as for myself, I'm Jack Mannino. I'm the guy in the middle right there. It's a couple years ago. So Mobile Security Project leader. Do mobile application security stuff back on the East Coast. Have a practice back there. Like messing around with Android whenever I have a little bit of spare time. Enjoy ripping apart some apps.
My name is Mike Zusman, also a co-leader. We started the project back in about, what was it, Q1?
End of last year.
Yeah, and end of last year into the first quarter of this year. And I actually went to the OWASP Summit in Portugal this past spring. I believe it was in the spring. And we really kicked off the initiative to start honing the OWASP Mobile Top 10 there.
My name is Zach Lanier. I'm a principal consultant with the Intrepidus group. I just became a co-leader of the project a few months ago, so we've kind of been hammering this out, and Jack will explain a little bit more about the history of the project.
So the project started towards the end of last year, and really the initial motivator for the project was coming back for like Black Hat and DEF CON last year. There were a lot of talks, talking about how broke every application like out there is, the platforms suck, developers are idiots, the usual stuff, but really nothing anybody could take back with them the next day of work and actually go and build a better mobile application. So that's kind of where this project came from. So like on the left, well, the right hand side to you guys, is just some of the things we have underway right now. So obviously we're talking about the risks today. We published some controls. There's some stuff out there for training. So there's the iGoat project, which actually he's not here today, but imagine WebGoat for iOS, that's what it is. There's the Goat Droid project. It's very similar for Android. And then hopefully like in the coming months, we're actually going to start taking the stuff that's out there and start drilling into like really platform specific guidance. If you are interested in contributing in any way, shape, or form, we have probably more stuff that we want to do than people at this point. If you want to get involved, just please come up to us, email us, get in touch somehow. We'd be happy to have you.
Sure, just to follow up on that, I mean, pretty much any initiative you see in the traditional OWASP avenues, we can have a mobile version of that. So there really is a lot of opportunity to contribute and a lot of work that needs to be done. We're going to touch a little bit on the mobile threat model now. To be honest, covering the mobile threat model could be probably a 90-minute presentation in and of itself. And we've consolidated that to 3 slides. And the reason why we're just going to discuss it now is that there are some people who say, why do we need the OWASP mobile project? Why can't we just have traditional OWASP cover this stuff? And the truth is that there are a lot of big difference between the typical web application threat model and the mobile application threat model. We'll touch on some of them here. Mainly, your platforms are going to vary with mileage. On the server side in the web application world, we've got things pretty much standardized, at a high level. But for the most part, anything that's going on the server, we control. What's happening now with these, in mobile is essentially we've kind of given the developers the responsibility of now writing the browser, as well as the server-side component of everything. So they need to write their own browser, a client application, and they need to understand the platform because platforms are going to be different. iOS is a lot different than Android, and there are things you need to be aware of when coding for a certain platform that can introduce security vulnerabilities. One example that comes to mind is the screenshotting of an iOS application that can potentially store sensitive data, when you close your device or go to the home screen. That's just one example. Also different from the web application world are the traditional use cases. or typical use cases. The mobile device, it's in your pocket, it's with you all the time, and it's got access to a lot more data than your web application does, or the web browser does. It's got direct access potentially to your client information, to your phone state, to your SMS messages, to your location. It's essentially a tracking device that's with you all the time, which is a lot different than a web browser or a traditional web application. But at the same time, we still need to consider much more than what's going on the client side. There are a lot of back-end remote web services now. You can sync data seamlessly from your device up into the cloud. So how do we protect that data? How do we protect personal data as opposed to corporate data that may be on the same shared device? So there's a lot of questions there. We can also talk about the actual architecture of mobile devices. It's no longer just an application talking over the internet to a web server. Now we've got the broadband connection through the carrier where we're talking to the cloud. We've got all of the alternate communication channels such as SMS and phone that are on the device as opposed to just your internet connection. Then on the left-hand side of this image, we see other forms of data connectivity. We've got Bluetooth, we've got NFC, we've got Wi-Fi. All of those different interfaces for communication can affect the way you write your client application. Just a quick example of how that can affect how you code an application. We've seen apps that, hey, if they're talking over the phone's broadband connection, talking to the internet that way, they're fine, they're using SSL. But then there's some logic that says, oh, if we're on Wi-Fi, don't use SSL. So there are considerations like that, at design time, at an implementation time that developers need to be aware of. Not to mention the fact that there's a physical threat to the phone security. If you lose that phone, there can potentially be a lot of data on that device that can be easily accessed through direct access to the hardware. That's something you don't typically have to worry about with either a desktop machine. You're most likely not going to lose that. And even in a laptop, we have controls like whole disk encryption that can protect data at rest if the device is lost or stolen. So a lot more to be aware of on a mobile device. And just to represent all this information in another format, here we've kind of laid it out in a stride format. And as you can see, it can get very verbose and detailed very quickly. And that's why, one of the things we need to work on for the project is an actual, a detailed mobile threat modeling project within OWASP Mobile. And like I said, this can be a 90-minute talk in and of itself. So with that, that's kind of the rationale. Now we'll jump into the top 10 risks, and I'll throw it back to Jack to start that off.
Cool. So part of everyone came here for, right? So the top 10 risks, one of the challenges was staying as platform agnostic as possible to kind of sort of make everything relevant across the platforms, but not being too generic where we were saying things like, bad security issue and stuff, right? So it still has to be useful. We focused on broader areas of risk, vice, individual vulnerabilities themselves. So, cross-domain, something, cloud hopping, blah, 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 blah. We didn't get that granular, but we kind of sort of broken down into areas of risk that encompass all those things. There are a lot of people that actually helped out with just coming up with this. We're going to post those probably next week to the wiki as well, just so they get their fair share of credit. So here's where we see the top 10. Now keep in mind, this is also a release candidate. So we're going to open it up for like 60 days, similar to what they did with the web top 10 a couple years ago. We really want feedback. I mean, if you guys are out there testing out, by the way, how many people actually test mobile apps and the security? Okay, cool. All right, yeah, so cool. So I mean, if you guys have anything to add, if you think anything just doesn't belong up there, it should be higher and lower on the list, just please, we really need the feedback. So first up, insecure data storage. So this applies to stuff that's on the device, but we're also considering the stuff that's on the device that ends up, say, being synced to, say, at some point the iCloud, or insert anything else up here. Also, if you're backing up data to, say, Google's Android backup services, or up in, at some point that data is going to end up somewhere that you just don't control it. Whether it's going to be in local backups to the cloud, people are going to lose their devices. You really have to consider what you're putting on devices. Now the challenge is that, I mean, if you don't cache anything on the device, you don't store anything, well, if someone's on the train or they're on a plane or something like that and they need to get that data and they can't get to it for hours, they're going to be pretty pissed. They might find another app to use. So you have to balance, those usability things with security. But at the same time, I mean, there's going to be compliance requirements, and you shouldn't be storing credit cards, SSNs, stuff like that. You should keep off there. Some platforms do a better job of providing stuff, like BlackBerry kicks everybody's ass in terms of like encryption and stuff like that in devices. I mean, iOS is a little better, and Android's like you're pretty much on your own. So here's an example from last year, the Citibank app. Everything you could possibly do wrong, they did. So I mean, they were storing account information, really bad stuff. And here's an example of something that you'd think this is ridiculous, but it's extremely common. So here's, this is actually like a screenshot from GoDroid. So here's remember me, and then here's, world readable, because files really need to be world readable. And you've just, broken the security model of how files are protected and stuff like that. Here's username, password, and then you do that, and then you end up somewhere down in the fire. So the recommendation is store what's really necessary. I mean, if you're going overboard, common sense is usually going to prevail 9 times out of 10. If you're using something like the SD card, or it's a different file system, it's not protected the same way that stuff's stored internally. So you definitely don't want to do that. And leverage what's there for the platforms. Some platforms do a better job. Hopefully, as Ice Cream said, the next couple versions of Android come out, they're going to get better, hopefully. But regardless, whatever's there for the platform, definitely take advantage of that.
The next one is a personal favorite of mine, and we kind of just randomly hashed out who was going to talk about which risk, and I'm really glad that I got to talk about this one. Because pretty much every mobile application that's useful is really just talking to something else on the back end, something out in the cloud. Usually it's some sort of web service, RESTful web service, or even just a web app. Maybe it's doing some screen scraping. So really, what we come across are a lot of the traditional OWASP top 10 sorts of risks and vulnerabilities. For example, and it was kind of funny to me, I'm recently looking at a mobile application, and it was with an organization that had a fairly mature web AppSec initiative going on. But you hear mobile, and all that stuff kind of goes out the window, and started looking at the server side of the app, which initially wasn't even necessarily considered in scope, but is obviously critical because that's where all the data is stored. That's what the mobile client is communicating with. And there was just no state. They weren't even using session management. They turned it off in WebLogic. And it's kind of things like that that just make you scratch your head. These developers, they heard mobile and they just went down a completely different path and ignored a lot of lessons that we've already learned. A lot of other, some other things we need to be aware of. There's this idea that we can trust the client in mobile, and we can put, make access control decisions in the client code. That's just not a good idea. If it's on the client, it's accessible by an attacker, it can't be trusted. All that stuff needs to be baked into your server side, into your server application. And what does this ultimately result in? SQL injection, forceful browsing, direct access to all sorts of things on the server side that you shouldn't be able to access. Interestingly enough, when the iPads came out and the first iPad hack was publicized, it wasn't necessarily a direct hack on the iPad itself, but the bad guys, or the internet trolls as they've been described in the media in some articles, basically they were able to sniff traffic and see what systems the iPad was talking to. And I think they found some pretty textbook direct object reference and parameter tampering in a URL that just let them pull data, increment an ID, from 1 to 1 million or whatever, and pull down records of iPad subscribers. So there you go. It was in the media, it was an iPad attack. It was mobile, but in reality, it was just poor practices on the web application, on the server side. So really, I wanted it to be pretty terse, and number 2 in the OWASP Mobile Top 10 was just please see OWASP Top 10 and OWASP Cloud Top 10. And really, you need to just directly address these sorts of vulnerabilities in your mobile app assessments. And also at design time, that's when it's really important, because for whatever reason, at design time, when people hear mobile, they're going to go down a different track. They think it's different, and again, they throw out a lot of what we already know. So prevention tips, I mean, it's pretty basic. You know, get involved at design time if you have that opportunity in your organization, and really push the other OWASP resources that are available.
So number 3 on the list is insufficient transport layer protection. So kind of what the example that was given earlier was an app that, and I think we'll highlight it here in a second, that would switch from using SSL over the carrier's network to not using SSL or TLS on over Wi-Fi, because that's probably someone at home, so it's considered a trusted network. So oftentimes we will see people who just simply disregard encryption altogether because they just assume it's going to be over a trusted network, or in some cases over the carrier's network where you know, it's in control of another entity, so let them handle all the crypto and controls around that. Excuse me. One of the other issues that often happens is ignoring the chain of trust in SSL cert validation, or simply just completely disregarding any errors that might come up around invalid certs, or simply switching over to something like plain text transport for if SSL ever fails. So obviously this lends itself to things like man-in-the-middle attacks. One of the examples that I had actually given previously in a couple of talks that was really silly was the Foursquare app for Android, which has now been, for some reason, considered deprecated, used to send, would actually authenticate over using HTTP basic authentication over non-SSL encrypted channel. So if you're at Starbucks, you go to check in on Foursquare, and somebody man in the middle's you there, then they can check in, check you in at strip clubs or whatever. So, and everyone uses Foursquare, don't lie. So the example that I was referring to earlier was Android client login security flaw. Basically what Google was doing was for certain applications or certain services that they would sync from Android handsets up to their services. They were encrypting most of them, but not all of them. And again, if they were over Wi-Fi, they would fall back to plain text for certain services, such as PCASA. So people could actually, attackers could actually pull down the token that was being used to, for like the session token, and then you reuse that for other services. So yeah, this is basically what I just said. So obviously to help mitigate this or prevent it altogether, anytime you're doing anything that is sensitive, such as authentication or transmitting any sensitive data, use appropriate SSL or TLS. And I actually see someone in the back who can probably tell us why SSL is broken. But regardless, if possible, encrypt anything as much as you can, or at least use something that will keep that data safe leaving the device. And don't assume that even the carrier's network is necessarily trustworthy, as we've seen where things like GSM have been broken. We can't necessarily trust that network to be safe. And also validate that certificates are actually legit, and don't just fall back to plain text transports for failures.
Next up, we have client-side injection. So we grouped kind of every kind of injection under here. So whether it's HTML, script injection, SQL injection, we just label this client-side injection here. So some things, cross-site scripting, I mean, applications, for starters, every single mobile device has a browser. And then a lot of applications will, they'll integrate like some web stuff and some, application stuff. So, obviously you have a mishmash of technologies there. So SQL injection on the mobile devices, it's not as ridiculous as like, say, owning an Oracle backend and having access to all kinds of, really rich, powerful things to do. But at the same time, you can still tamper with data, you can still read stuff that's on the local device. Which also ties into other things. If you're making some kind of security decisions based on the information that's, say, in a database, something like that, well, you can find creative ways to kind of pivot and do some bad stuff. The interesting thing is that just how some of this stuff is used. So here's an example of something that's really, really recent. And by the way, XSS makes Skype better or something like that. But anyway, so this was actually pretty bad. So then this XSS allowed you to rip somebody's contact list out from their iPhone. And here's an example of something. So on Android, you're allowed to bind basically like it's JavaScript interfaces. So you can bind a Java Java class, Java libraries, and everything like that to JavaScript. So when it's actually executed and ran in the web view, in theory, cross-site scripting right there. So you just have to basically do like window.smsjs interface dot send SMS, and then the appropriate parameters, and you fire enough SMS messages at that point. So it's interesting because you have one issue which leads to different issues based on like the rich features of the platform. So the recommendation there is don't ever tie like SMS or something like that to JavaScript, because you're nuts. And I don't know if I could be your friend at that point. But I mean, we know a lot about how to fix these things. It's just a matter of just getting people to actually do it. So I mean, if you're pulling untrusted data from somewhere else and you're populating, you're getting some JSON stuff, and you're like, okay, I'm going to populate a web view or stuff like that. Do your same due diligence. I mean, properly encode it in the appropriate context, et cetera, et cetera. If you're, using SQL, anything, if you're concatenating, well, you probably haven't been paying attention to anything anybody said for the past, how many years, right? And last but not least, just really think about what you're tying. And so we're going to get into like another issue where you might not have control, but at least if you have control of the application, just really think about what you're tying to some of these web pieces of functionality.
All right, poor authorization and authentication. I don't know how many apps I reviewed where basically the app was sending the phone number of the device to the server, and that was authentication. I guess there's a number of challenges we have to deal with in the mobile space, in that the keyboards are much smaller. It's harder to enter a username and a password. We don't necessarily want to store that information on the device, and some people know that, others don't. They choose to store that information on the device to make it easier on the users. So what happens is we kind of push developers towards finding an easier way, and they'll use data such as the phone number or other unique device identifiers like IMEI or UDID on iOS to authenticate the device to the banking application, to whatever application is enabling access to sensitive data. So the concept of strong authentication kind of goes out the window in a lot of cases. What does that translate to? Well, a small key space. These identifiers are easily brute forceable, and next thing you know, you can iterate through everyone's account in the system. Same thing goes for the authorization. I touched on some examples of baking authorization and access control decisions into client-side logic. Just a couple weeks ago, we were looking at an app where the server sends down a token that says, okay, you're admin, and all of a sudden, new admin functionality opens up in the client device, and there were no other server-side checks going on to enforce that. So, you push this client application down to the user. It needs to have the functionality baked in, whatever the higher privileged functionality is. You have different functionality for different roles in the app. You kind of have to accept the fact that the user or an attacker who's reversing this app is going to see, oh, there's this hidden functionality I can get to. But on the back end, you need to remember that you need to perform the access control there. Access control doesn't end at the client. It needs to be enforced on the server. So there are, many ways in a poorly implemented mobile application that you can bypass authentication and assume the identity of other users and gain unauthorized access to data in terms of horizontal privilege escalation, as well as vertical privilege escalation, because developers assume many times the design requirements that the developers are following aren't clear or direct enough, that all this access control can happen on the client side. This is just an example of using a unique device identifier to authenticate the device. So we see that we're just looking up the device ID to see if it's permanently authenticated or authorized to use the application. And if the device ID is whitelisted, we give the guy a valid session token. So that's not the way you need to do it. You need to use strong authentication, strong credentials, secret data that is not easily brute forceable or discoverable. Contextual information can, enhance the authentication experience for a user, but really only as part of a multi-factor implementation. I mean, you need to have multiple factors of auth. Out of band doesn't necessarily work if the out of band mechanism is on the same device. For example, sometimes we see that username and password is sent to the server, and then the server sends back a valid session token or some other piece of data key to session management over SMS. Okay, that's out of band. If you're sniffing traffic on, at some point, you're probably not going to see that SMS message go through. But if you've already owned the device and you can create an event handler that's looking at all incoming SMS messages, well, that rogue application on your device is going to see that SMS. So out of band really needs to be out of band if you're going to go that route. And the real important thing is never use a device ID or a subscriber ID as a sole piece of authentication data. You need to have multiple factors. One other thing I just want to touch on before we go to the next one is, this was actually the first slide that didn't have a relevant news article, but one of the higher level risks that we see, there seems to be much more of a reputational risk for organizations that are pushing out mobile apps. You can do something really simple, such as, don't turn on strict certificate validation checking for your SSL connections, and next thing you know, you're written up in the Wall Street Journal, and your organization gets a black eye. So one of the things that Arian Evans was talking about yesterday was, how do we communicate to senior management all these problems to help get budget? Well, it seems like in the mobile space, it's much easier to get written up and have that widespread reputational damage. So that's just kind of food for thought out there, in terms of how do you relay this information up the chain and get resources to do not just mobile application security, but application security in general.
So actually, I wanted to add to that too. That also, M5 also applies to servers authenticating themselves to the client as well. So making sure that the client can actually know that the server is authorized to do an action. One of the examples that I wanted to give really quick was an app where it was an endpoint security solution for mobile, and it would issue remote wipe commands over SMS. And it took about a very short period of time to figure out that the actual authenticator was the phone number concatenated with a static string and MD5. So if you could just figure out what your phone number was, or the bad guy knows what this string is, makes the digest of that, sends an SMS to your phone with that and the command to remote wipe your device gets blown away. So authenticating the origin of messages, authentication should also, and authorization should be built into the client as well. So improper session handling. So this kind of goes back to some of the authentication and authorization issues as well. Typically, because of usability requirements and because we can't necessarily guarantee the fidelity of a connection that a device has, people we often see will put a longer, like a token with a longer lifetime, or they'll store the token somewhere insecurely, kind of going back to some of the other examples earlier. Or they will use homegrown session management, or not use session management at all, like Mike was saying. So one of the things that we also see is people simply using a device ID as a session token, and well, that session token never really expires because it's a device ID, and as mentioned before, will persist. One of the things that is mentioned in here is OAuth, which I think personally is a really great thing. It's not foolproof, but it does definitely address some of the traditional issues around mobile session management. So some of the things that we would recommend is expire tokens. These are web services. They do have the ability to actually expire tokens. It kind of sucks that your user might have to put in a username and password again, but if your application is sensitive enough, it wouldn't hurt to do that. Something like OAuth, for instance, does support the ability to actually remotely revoke tokens, or through typically through a web UI. If any of you have ever used Twitter, I'm sure at least 2 of you have. There's actually an interface where once you've granted a third-party application access to your account, you can actually later revoke that authentication token that app will use to access your account. So having an interface like that to be able to turn that off is also recommended. Obviously, typical session management, session handling things apply here. Don't use easily guessable or poorly generated session tokens. So that kind of goes back to traditional OWASP top 10 stuff.
So next up on the list, and this is something that really applies for the most part to iOS and Android the most. So security decisions via untrusted inputs. So on iOS, you have the concept of URL schemes. So for example, here's a quick example just for anyone who's not familiar with it. So right there you have an iframe, you have Skype, phone number. So that's an example. So when the OS, it sees that, okay, something's called with Skype, it's going to fire off the appropriate application that knows how to handle that. So the issue with this in particular was that it would actually allow, so somebody actually just iframed it like that, and it hit the Skype application, and the application didn't say, hey user, do you really want to make this phone call? It just let the phone call go through. That's definitely a problem. So going back a slide. So yeah, Android, something similar. I mean, not going to get into intents and the whole permission system and how that works between components and stuff like that. But in the Android world, anyone can just gray out of the vanilla out of the box. Any application can start like an intent. With if you don't have the permissions around, or not intent, an activity, right? So an activity is like if you open up your application, you're looking at an activity. It's a single thing you can basically do. So if you're firing off, say for example, like as soon as that activity fires off, you're firing off like saying like an async task or something like that does something really, really bad. That's not good. So if another application would say start, delete account or whatever, or make like, obscene transfer or something like that. You're not doing additional things to validate, who's calling it, does the user really accept this? That's an issue. So there's a really rich, and we could spend a lot of time in this, but at least from like an inter-process type thing, application, there's a really rich attack surface for this kind of stuff. And we just hit that. So the recommendation is, check who's calling it. So I mean, there are permissions like, and if it's something sensitive, go the additional 2 or 3 steps. I mean, the same thing you do, on a conventional web application. To say, for example, like change user settings, you might make them re-authenticate or something like that. You definitely need those additional, checks and stops in place. Otherwise, you're just going to set yourself up for failure. Yeah, so not gonna hit that. That's one that I could probably like really get out of control with, but we're not. So, gonna turn that back over to.
Yeah. So side channel data leakage. This is pretty interesting. We've seen like typical issues around people storing too much client side in web browsers. That's kind of a well understood science there. But of course, as Mike mentioned earlier, that screenshot issue on iOS, where by default, when you hit the home screen or turn off the device or lock the device, it actually takes a screenshot of the app. So if you have that app, that screenshot cache can be recovered. So if you had a screenshot up with a login prompt or an account transfer prompt or something, that would be a side channel for data leakage. Obviously, web caches are still a concern on mobile devices and mobile apps as well. There are issues around keystroke logging. For instance, in Android, you can install things like Swipe, which is an alternative keyboard. There are also spyware apps, legit spyware apps that will install an alternative keyboard so that you can watch what your teens are doing and what Facebook things they're doing and entering into SMS messages and whatnot. And that actually stores a log somewhere of all the keystrokes and also syncs it somewhere else. So if an attacker was able to enumerate the apps installed, they could probably guess the location of that log. Also, one of the things that we see a lot are a lot of debugging messages being put into logging facilities on mobile devices. The guys over at Lookout actually did a talk last year at Black Hat where they in one of their examples they said, what's the minimum amount of things we can do to successfully exfiltrate data from an Android device? So what they did was, one of the examples they gave was have an app only request the read logs permission. And then they just looked for certain things that were hitting the log, and then just popping up the web browser and HTTP posting or HTTP GET to an endpoint they controlled with information they were pulling from the log. So apps will oftentimes log very complex or very sensitive information to debugging facilities. And then of course temporary directories where you might be storing files for that might otherwise be removed later, but could have sensitive information in there. And of course, third-party libraries. One of the examples that comes up typically is third-party ad libraries, which leak a lot of information about the user location information, device information. That's something that you would want to consider. Know that if something like Pandora, it was an example where it was leaking a lot of information about the users, much to their ignorance. So, be aware of what they do. And here's an example of a logging issue in iOS, where Jack, this is your example of the iOS one. Oh, so in this case, basically what it's doing is actually just writing out to a warning log the information that's being put into a login form here. So some of these logging facilities are pretty easy to access from a seemingly legitimate app and would otherwise be really easy to pull sensitive information out of. So don't log credentials, don't log PII, don't log. In some cases, I've seen developers actually log. They'll otherwise obscure their code really well and use things like ProGuard, which is reversible but still is just upping the ante. But then in the log messages, they'll show exactly how their HTTP requests are constructed. So then using that information, you can easily attack the back end. If you are on iOS, disable screenshots for your app, or just don't store information that, or put information that would otherwise be included in a screenshot when the user hits the home screen. Remove any debugging messages that might be put into your app before you release it to production. So a lot of typical kind of best practices around software development here, and then also third-party stuff.
So crypto is really hard. I don't know if anybody follows any of the SSL stuff going on, but even certificate authorities who have tons of money to spend on doing it right can't seem to do it right. So how this all trickles down to mobile app developers is, well, crypto is hard. There's a lot of opportunities for failure. And the two primary categories for failure, much like in the web application world, are either using broken implementations or implementing known algorithms improperly, or just deciding to roll your own crypto and create something that's, in many cases, trivially defeated. Other common mistakes, encoding does not equal encryption. There's still people out there who think base64 encoding is encryption. That's not the case. Obfuscation is not encryption. Just swapping bytes and mixing things up, that's going to be figured out. And serialization does not equal encryption. Just putting something into a not as easily decipherable data format is not going to protect your data from somebody who has a vested interest in accessing it. And when we're talking about all this, kind of reversing a homegrown crypto algorithm, you need to remember that on many of these platforms, it's somewhat trivial once you have the application in hand, because you downloaded it from the marketplace or from your organization's website, that it's easy to bring it down to either bytecode or in some cases source code, and actually reverse the logic that's baked into the app. I've seen many examples of this. This one was kind of interesting. So this was actually a BlackBerry application that was designed to basically sync images and other data up into the cloud. But the developers, they actually had to write this application to work on like version 4 of the BlackBerry API and version 5. And one of the 4.6 dot whatever actually had a bug in the SSL API. Like I said, crypto is hard. This is in RIM code. This wasn't something that the developer, a bug that the developer introduced. He had to work around an implementation flaw in the platform. So the actual bug in the platform was that a post over HTTPS over a certain number of bytes would just fail for no reason, seemingly. So what they realized was that, okay, they knew they needed to protect this data somehow, so they decided to implement an asymmetric crypto implementation using triple DES. But what they did was they put in a hard-coded static key that would have been the same on any installation of the application. So if 1 million people downloaded this app and were uploading data on this version of BlackBerry, then all that data traversing the wire would be easily recoverable because the key was easily recoverable from the Java bytecode. which was you get the Java bytecode from a RIM cod file using a utility named codec, which is somewhat flaky. Sometimes it works, sometimes it doesn't. Fortunately, it worked here. So this example just goes back to show you you really need to understand the limitations of the platform. The platform developers make mistakes too. So how did we fix this? And it was kind of interesting. Really, I told them they needed to use asymmetric cryptography, where they could still use the server's public key to encrypt this data and send it up over the wire. For whatever reason, they didn't decide to go that route, and they actually wrote a whole new web service that the application could pull to retrieve a new symmetric key. And the funny thing was, at first, that symmetric key was also static. So everybody was just getting the same key. So then they built a whole new, a lot of additional server-side functionality to map the new symmetric key to the session. So again, I mean, it was better, I guess, but still overly complex. Interestingly enough, recently I've been looking at I looked at a BlackBerry application and a Windows Phone 7 version of the same application. And in the BlackBerry application, they were using keys generated on the device, not necessarily using Java Secure Random. They needed to encrypt data, so they were doing it okay, but one of the other problems I flagged them for, the default, what is it on RIM? It's the AES encryptor engine. By default uses electronic codebook, ECB mode for encryption, which you can go to the Wikipedia article, and the example they use is an encrypted image of the Linux penguin, and you still clearly see the Linux penguin because there's no interference introduced into the actual encryption process. So that's the math stuff that I'm not qualified to talk about. But it could have very easily just implemented CBC mode, cipher block chaining, and using initialization vectors, which they just needed to do that. Funny thing was, on the Windows Phone 7 app, by default, and I did some research just looking into that, all the code examples used CBC mode, used IV, used a stronger mode of encryption. So just between the two versions of the same application, the Windows Phone 7 was a little bit better out of the box. That developer had, in my opinion, they had a better chance of success just based on the platform and the resources available. So some prevention tips. Again, don't roll your own crypto. Crypto is hard. That's something we've been harping on for years. Don't necessarily store the key with the encrypted data. You need to utilize the secure storage mechanisms of the platform. So in Windows Phone 7, there's isolated data storage. There is, the name escapes me of the RIM version of isolated data storage, but there's a way to use code signing to actually restrict access to a data store only to that application. It's a little bit more complicated than on Windows Phone 7. But basically, you want to make the key hard to get to from a rogue application. So if the device falls into the hands of an attacker, or the application falls into the hands of an actual person, he's going to get at the key. But what we can prevent using the appropriate data storage mechanisms of your platform is a rogue application from being installed on the device and just being able to access the encrypted data and access the key. So we need to protect the key from programmatic attacks. And again, we just need to take advantage of what the platforms already provide and need to make sure that our developers understand what the platform provides.
So last up, number 10. So for this one, we distinguish between what's stored on the devices as insecure storage. So if it's stored to the file system external to the application, then that's insecure storage. If it's hard-coded into the app, in the binary and compiled and all that good stuff, then we're grouping that under number 10. So some platforms, it's definitely a bit easier to reverse an app, back to actual code than others. But at the same time, in the end, it's very similar, some of the stuff you see, to what happened when people started pushing more logic down to the browser. So the whole Web 2.0 Ajax and whoop-de-doo thing happened, and people just lost sense of good judgment. They said, oh well, just push down to the browser. Who cares? It's not visible to the user. It's it's in a hidden form field, so what can go wrong, right? So very similar. I mean, you'd be amazed at the crap that people are just like putting into their apps. Like it seems a little ridiculous, but it's really not. This kind of stuff, and it's like, oh, hey, no, don't worry, it's in the app, and no one's going to get to it. I mean, anything just like a browser-based application. I mean, if you're giving it to the client, if you're, a desktop, I mean, in the end, it's a piece of software. If someone has it in their possession, I mean, eventually, they're going to get what they want out of it. The recommendation, it should actually put like number one, just use common sense, use your brain. If it's really sensitive to your business, whether it's from, say, an intellectual property perspective or from a security perspective. So I mean, if you're, putting creds, you're putting, sensitive endpoints that, might have taken like 20 years to, brute force enumerate and stuff like that, you messed up. Recommendation, keep it out of the application. If it's not necessary, it doesn't belong in the binary. So with that said, we have about 4 minutes left, so really quick wrap up. So yeah, we're going to keep it open for about 60 days. If there's anything you don't agree with in there, come talk to us. In the next phase, we're going to try to get more. We got some metrics. I mean, we got a good amount of feedback, but we really want, from people that are doing a lot of assessments and seeing a lot, and even people that, internal dev shops that are, seeing, here's issues and, across our portfolio applications. We're really interested to just kind of share data across different industry verticals and stuff like that as well. We're going to try, maybe it's going to happen, maybe it's not, but to go with like a 12-month release cycle for this. The interesting thing is that, just how fast these platforms are moving along. New things. I mean, we haven't seen, NFC. That's going to be the next big boom, and people are just going to lose their brains again when they start rolling out NFC apps. So we want to try to keep it as current as possible, just so people are working with data that's actually relevant for the current platforms. So conclusion. So I mean, we've started to identify these issues, but the next set of things we need to do. So we really need to start getting into individual platforms themselves and really drilling down some really good practices. There's been talk about doing, like a SAPI for Android, a SAPI for Objective-C, iOS. So I mean, these are good things. I mean, ultimately, the more of these tools we can put in the hands of developers, in theory, they'll start building better applications. So with that said, that's all we have. Thank you.